Momentum and impulse. We have two curves right in front of us, A and B. They're identical, as you can clearly see. They both have a mass of 2000 kgs. I want you to think of something. Let's say you had to stand in the path of one between the two cars and push the car until it comes to a complete stop. For car A, it is moving with a velocity of 10 meters per second. And then car B is moving with a velocity of 20 meters per second. If you had to push one between the two cars to a complete stop, which car would you choose? They have the same mass. They differ in velocity. Car A has a velocity of 10 meters per second, while car B has a velocity of 20 meters per second. Which car would it be easier to stop between the two? Obviously, it is going to be car A because it has a speed of 10 meters per second. It has less speed compared to car B, right? So it would be easier to stop. Here we don't have identical cars anymore. We have car A with a mass of 1500 kgs and car B with a mass of 2000 kgs. If car A is moving with a velocity of 10 meters per second and car B is also moving at a velocity of 10 meters per second, then which car would be easier to stop between the two cars? It should be easy to see that car A would be easier to stop between the two cars, right? Even though they're moving at the same speed, car A has less mass, so it would be easier to stop because of the mass. If you ask a grade 10 learner these questions, they will probably get them right, even though they don't know the physics behind it. But in our case, we have to find out why that is the case. So let's go ahead and do that. Momentum is the product of an object's mass and its velocity. From the previous video, I'm sure you have seen that when you change the mass, something happens to the momentum. And when you change the velocity, the momentum also changes. So the formula we have for momentum is P is equals to M multiplied by V, where P is equals to the momentum. So P is the symbol we use for momentum. The SI unit is in kg meters per second. That will make sense very soon. P is equals to M multiplied by V. P is the momentum and M is the mass. In chemistry, the mass is in grams. In physics, the mass is in kg. Okay, so the mass is in kg. If you find that you're given the mass of an object in grams, you obviously have to convert it to kgs by dividing by 1000. That's how it works. And then V is the velocity in meters per second. Nothing new there whatsoever. V is the velocity in meters per second. So momentum is the product of an object's mass and velocity. Mass is a scalar and the velocity is a vector. So the product of a scalar and a vector will give you a vector. So momentum is a vector. We need to put into consideration the direction when we are solving our problems. So let's just recap. Momentum is the product of an object's mass and its velocity. P is the momentum in kg meters per second, M is the mass in kgs, and V is the velocity in meters per second. Let's take a look at these two examples. But before we look at the examples, there are some guidelines that we should always follow. The first one being that always convert the mass to kgs and velocity to meters per second. Like I've said, right? We need to convert the mass to kgs and the velocity to meters per second. That is bullet point number 1. And bullet point number 2, remember to indicate direction using a plus sign and negative sign. This is when you substitute, okay? And then the third bullet point, provide your answer with the unit and direction. we need to include the direction because momentum is a vector, like I have said. Okay, so that is the third bullet point. The fourth bullet point, if you obtain a negative answer for a vector, it only means that the direction is opposite to what you chose as positive. That's all it means, nothing more than that. So there we go. Those are the things we need to remember as we calculate. Okay, let's take a look at the first question. A dog with mass 30 kgs runs at a velocity of 45 meters per second. Calculate the momentum of the dog. Well, this is pretty much straightforward. The mass is in kgs, so no problem there whatsoever. And the velocity is in meters per second. So we're going to write our formula. P is equals to M multiplied by V. And then we're going to substitute. P is equals to the mass, which is 30, multiplied by the velocity, which is 45. This is equals to 1,350, the magnitude. We include the units, which is kg meters per second, and lastly, we include the direction. We need to give the magnitude, the SI unit, and the direction. The direction is in the direction of the motion, okay? But usually, when we solve problems, you're going to be given whether it's to the left, to the right, west, east, and so on. So that is the first question. No trickery there whatsoever. You should be able to make sense of that. And then the second question, a car is traveling at 60 kilometers per hour. If the mass of the car is 250 kgs, calculate the momentum of the car. Well, there's a slight problem. We have the mass, which is 250 kgs. That's okay, right? There's no problem there whatsoever. The problem arises with the speed or the velocity. It is 60 kilometers per hour. And we need our velocity to be in meters per second, not kilometers per hour. So we need to convert that 60 kilometers per hour to meters per second. How do we do that? We divide by 3.6. If you divide by 3.6, you're going to get 16.66666. 6 recurring, right? So, right, you just have to, if your velocity is in kilometers per hour, you divide by 3.6 to convert it to meters per second. That's all you have to do, right? Not only in this problem, even if you come across a different problem, if the velocity is in kilometers per hour, you just divide it by 3.6 to convert it to meters per second. The mass is 250. There is no problem there. Okay, we multiply the two numbers and we have a momentum of 4,166.67 kgs meters per second in the direction of the motion. There we go. Momentum depends on mass and velocity. So if the velocity of an object can change, then the momentum can also change. Change in momentum. Let's go ahead and take a look at that. So delta P is equals to P final minus P initial. P final being the final momentum and P initial being the initial momentum. The SI unit is still the same because it's just momentum minus momentum, right? The SI unit is still kg meters per second. We need to remember that initial momentum, final momentum, and change in momentum are vector quantities. Direction is very important and should be included in your substitutions. So when you're calculating either the change in momentum, the final momentum, or the initial momentum, it's important to remember that these are vector quantities. We need to account for the direction. Change in momentum is related to Newton's second law. Let me show you why that is the case. Okay, Newton's second law. We know that F net is equals to ma. So we have F net being equals to ma. From vertical projectile motion, one of the equations we have is Vf is equals to Vi plus A multiplied by change in t. If we take a look at this equation and make a the subject of the formula, we're going to have Vf minus Vi being equals to A multiplied by delta T. Let's go ahead and divide both sides by delta T. If we do that, we're going to have Vf minus Vi divided by delta T being equals to A. What we want to do now is to substitute Vf minus Vi divided by delta T in place of A in F net is equals to Ma. If we go ahead and do that, we're going to have F net being equals to M. In place of A, we have Vf minus Vi, everything divided by delta T. If we multiply out, we're going to have the mass multiplied by Vf minus the mass multiplied by Vi, everything divided by delta T. What is mass multiplied by velocity? That is momentum, right? So we have momentum final minus momentum initial divided by the change in time. So F net is just change in momentum divided by change in time. Formally, we say that the net resultant force acting on an object is equal to the object's rate of change of momentum. This right here is very important. We're going to use it at a later stage for sure. Let's give these two examples a try and get familiar with the concepts. A tennis player serves a tennis ball towards his opponent. The ball moves through the air with a momentum of 11 kg meters per second east, right? It is a vector, so the magnitude and the direction. The opponent hits the ball back in the opposite direction, and the momentum of the ball changes to 8 kg meters per second west, right? And then the question, calculate the change in momentum of the tennis ball. So let's go ahead and take a look. We have the initial momentum. The initial momentum is 11 kg meters per second east, right? So in questions like this, we need to decide on a direction we take in as positive and a direction we take in as negative. Same way we do in vertical projectile motion. Well, let's take direction to the east as positive. If we take direction to the east as positive, then the initial momentum is 11 kg meters per second. And then the final momentum will be 8 kg meters per second to the west. So when we substitute that, we're supposed to put a minus sign because it is to the west and we're taking direction to the east as positive. So momentum final is 8 kg meters per second to the west. What are we interested in? We're interested in the change in momentum. We know fully well that this is equals to momentum final minus momentum initial. So the final momentum is 8 kg meters per second to the west. So that will be minus 8. This is because we're taking direction to the east as positive. So we have minus 8 minus the initial momentum, which is positive 11 kg meters per second to the east. So what is minus 8 minus 11? That is minus 19, right? So this is just 19 kg meters per second to the west, right? So this is our final answer. We have the magnitude and the direction. So here we had a negative answer, but we know that the negative is just an indication of the direction. So we need to code again without a negative sign and then give the direction, just like I'm doing right here. So it is 19 kg meters per second to the west. So there we go. That is how we can solve a problem like that. The second problem, an arrow is shot with an initial momentum of 20 kg meters per second towards the target. It penetrates the target and its momentum changes by 4 kg meters per second. Okay, in the opposite direction, right? Calculate the final momentum of the arrow. Okay, so we are given the initial momentum. Again, let's take, okay, here we don't have east or west, right? We have towards and away. So let's take towards as positive and away, or in the opposite direction, as negative. So an arrow is shot with an initial momentum of 20 kg meters per second. So the initial momentum is 20, and then it penetrates the target and its momentum changes by 4 kg. So we have the change in momentum, which is equals to 4 kg meters per second in the opposite direction. So the change in momentum is minus 4. We are interested in the final momentum. So we're still going to use the same equation. We're going to have the change in momentum being equals to momentum final minus momentum initial. We have the change in momentum, that is minus 4. We have the final momentum. Well, we don't. That's what we're interested in. So momentum final, and then minus the initial momentum, which is just 20, because it is in the direction we're taking as positive. So minus 4 plus 20, because we're going to add 20 on both sides, right, to make the final momentum decided on the formula. We're going to have 16 being equals to the final momentum. So the final momentum is just equals to 16 kgs meters per second towards the target. It's positive, so it must be towards the target. Let's talk about impulse. Impulse is derived from Newton's second law. F net is equals to ma, and in place of a, you substitute Vf minus Vi divided by the change in time. Okay, so from Newton's second law, we have the resultant force, or the net force, being equals to the change in momentum divided by the change in time, of which we know that the change in momentum is the mass multiplied by the final velocity minus the mass multiplied by the initial velocity, everything divided by the change in time. Obviously, we can cross multiply. If we cross multiply, we get the resultant force multiplied by the change in time being equals to the change in momentum. So the resultant force multiplied by the change in time is what we call the impulse of a force, right? Of which the impulse of a force is equals to the object's change in momentum, right? Of which the force is applied on. We need to remember this. The impulse of a force is equals to the change in momentum of an object. When a force is applied to an object for a short space of time, it will bring about a change in the momentum of the object. Let's dive deep into impulse by studying with the definition. So the impulse is the product of the force applied and the contact time. That is the impulse. The impulse is the product of the force applied and the contact time. So since force is a vector quantity, impulse is also a vector quantity, and its direction is the same as the direction of the force, right? You will see this in detail when we start solving some problems. Like we've said before, impulse is equals to the change in momentum. Impulse is very important when it comes to safety of vehicles. Let's take a look at that. So impulse and safety considerations. To avoid more serious injuries, if an object can be stopped over a long period of time, a smaller force will be required and thus less damage caused. Because we're saying that F net is equals to the change in momentum divided by the change in time. So if we increase the contact time, F net is going to decrease, right? They're inversely proportional to each other. Okay, so this occurs in the cases of airbags, seat belts, and arrestor belts for trucks and planes. We have a ball moving at a velocity of 30 meters per second. It has a mass of 0.5 kilograms. After it gets hits, it moves to the opposite direction with a velocity of 40 meters per second. The first question is saying, let's find the impulse applied by the bat. And then the second question, determine the force applied by the bat to the ball if they're in contact for 0.1 seconds. Take original direction as positive. So let me show you how we can answer the first question. We know fully well that the impulse is equals to the final momentum minus the initial momentum, which is just mv final minus mv initial. We know that the mass of the object is 0.5 kgs. There we go. And the final velocity is 40 meters per second in the opposite direction, right? So that is going to have a minus sign. So that is why we have 0.5 multiplied by minus 40. And then the mass of the object still 0.5, and its initial velocity is 30 meters per second in the original direction, of which we are taking as positive. If you put that in your calculator, you should get minus 35 kgs meters per second. This is to the opposite direction. So now that we have the impulse, it should be quite easy to calculate the resultant force, because we know that the resultant force is the impulse divided by the change in time. So let's go ahead and see how that will look like. As you can clearly see, the impulse divided by the change in time. So we have minus 35 divided by 0.1, which is minus 350 newtons. Explain the meaning of the term elastic collision. So an elastic collision is a collision in which both the total momentum and the total kinetic energy are conserved. A collision in which both the total momentum and total kinetic energy are conserved. Not so complicated. So that is 4.1. Let's go ahead and take a look at 4.2. So in 4.2, we are asked to calculate the velocity Vy for 5 marks. So let's go ahead and take a look at our question statement and make sense of the situation. So a ball X of mass 10 kgs is moving eastwards with a velocity of 2 meters per second. It collides elastically with another ball Y of mass 2 kg, which was moving with an unknown velocity Vy. So this is the unknown velocity Vy we're interested in, and that is in diagram A. Okay, we can see ball X with a velocity of 2 meters per second and ball Y with unknown velocity Vy. Immediately after the collision, ball X comes to rest and ball Y moves eastward with a kinetic energy of 36 joules. So X is now at rest and ball Y has a kinetic energy of 36 joules. So based on the variables we have here, there's two ways I'm thinking of right now that we can use to find Vy. Okay, we can use the fact that the sum of the kinetic energy before the collision will be equals to the sum of the kinetic energy after the collision, because the collision is elastic. Or we can use the conservation of linear momentum, because if the collision is elastic, then the momentum will be also conserved. Okay, but if we use the conservation of linear momentum, we have to convert these 36 joules to velocity. Okay, but if we use the conservation of kinetic energy in an elastic collision, we would have to convert these 2 meters per second to kinetic energy. So whatever way we use, we must get to the same answer. Let's just go ahead and use both and see what happens. So if we use the kinetic energy, because our collision is elastic, we can say that the sum of the kinetic energy before the collision should be equal to the sum of the kinetic energy after the collision. Okay, so like I've said previously, our first statement should be that the kinetic energy is equal to F mv squared. Okay, so now let's go ahead and calculate the sum of the kinetic energy before the collision. For ball X, as we can see on the diagram, we're gonna have F. The mass for ball X is 10 kgs, so we have 10 kgs multiplied by 2 squared, that is its velocity, plus the kinetic energy of ball Y. So we're gonna have F, the mass of ball Y is 2 kgs multiplied by Vy squared. Vy is what we're interested in. Okay, and then after the collision, ball X comes to rest, so the kinetic energy is 0 at that point. If the velocity is 0, the kinetic energy is going to be 0. So we have 0 plus the kinetic energy of ball Y. It is already given to us as 36 joules. So we can just go ahead and write that down. Okay, so let's go ahead and have a look. 2 squared, that's 4. 4 multiplied by 10, 40 divided by 2, or multiplied by a half, that is 20. So we have 20 half multiplied by 2, that will be 1. So plus Vy squared is equals to 36. So Vy squared is equals to 36 minus 20, that is 16. So Vy squared is equals to 16. So Vy is equals to plus or minus 4. But let's take a look at our situation and see what makes sense. Ball Y, initially it's moving to the west. Okay, we can make that conclusion because ball X comes to a stop after colliding with ball Y. So the Vy is 4 meters per second to the west. This is if we use the fact that the kinetic energy is conserved. We're going to have an answer of 4 meters per second to the west. So now let's go ahead and use the fact that momentum is conserved and see what answer we're going to get to. So let me get rid of all of this. So what am I proposing now? I'm proposing that we can easily say that the sum of the momentum before the collision should be equal to the sum of the momentum after the collision. Our objects are separate before the collision and still separate after the collision. So we're going to have mx v initial plus my v initial being equals to mx v final plus my v final. Okay, obviously we have the mass mx and my, okay, together with mx and my after the collision. The mass doesn't change. We have vi for our ball X before the collision. Vi for our ball Y is what we are interested in. Okay, that is our unknown variable. And then after the collision, we have Vf for our ball X. It comes to a stop, 0 meters per second. But we don't have Vf for our ball Y after the collision. We have the kinetic energy, so we can convert that kinetic energy to velocity. Okay, we know fully well that Ek is equal to F mv squared. The kinetic energy is 36 joules. This will be equal to F. The mass for ball Y is 2 kgs v squared. So 36 is equal to a half multiplied by 2, that is 1. So 36 is equal to v squared. So plus or minus 6 is equal to v. It is moving to the east. So we're going to have 6 meters per second east being equals to v. So there we go. We have the velocity for our ball y. So we can go ahead and substitute. We are taking direction to the east as positive, right? We're going to do that for all the questions that we are going to answer, unless the question says otherwise. Okay, so mx, that is 10. So we have 10 multiplied by vi, which is 2, plus my, that is 2. And then this vy is what we're interested in. Mx, that is 10. Final velocity is 0, plus the mass of ball y, which is 2 kgs. And then vf for ball y, we just calculated it. It is 6 meters per second to the east, and hence we're substituting it with a positive sign. So 10 multiplied by 2, that is 20. So we have 20 plus 2 vy being equals to 10 multiplied by 0, it's 0. 2 multiplied by 6, that is 12. So we're gonna have 2 vy being equals to 12 minus 20, that is minus 8. So vy is equals to minus 4, which is just 4 meters per second to the west. So there we go. We get to the same answer if we use the fact that momentum is conserved, or if we use the fact that kinetic energy is conserved. There we go. There's probably more options. There's probably another way you can use to answer this question. Okay, so that is 4.2. Let's take a look at 4.3. So in 4.3, the balls were in contact with each other for 0.1 seconds during the collision. Calculate the magnitude of the force that ball X exerted on ball Y during the collision. For ball Y, the initial velocity, which we just calculated, is 4 meters per second to the west. So 4 meters per second to the west. And the final velocity, we also calculated it in 4.2 when we're using the fact that kinetic energy is conserved. We found it to be 6 meters per second to the east. And then the mass obviously is equals to 2 kgs, and the change in time is 0.1 seconds. Yeah, the balls were in contact with each other for 0.1 seconds. So with this information, which equation can we use to find F net? Obviously, we can say that F net is equals to the change in momentum divided by the change in time. So the change in momentum will be the mass multiplied by Vf minus Vi, everything divided by the change in time. So the mass, that is 2 kgs, Vf is 6 minus Vi, which is minus 4. Okay, everything divided by 0.1. So let's go ahead and take a look. So we're gonna have 6 minus 4, so that is 10 multiplied by 2, it's 20, divided by 0.1 is 200. So we have 200 newtons. So there we go. This is the magnitude of the force that ball X exerted on ball Y during the collision. Product of mass and velocity, that is momentum, is the object's product of mass and velocity. That is 4.1. Let's go ahead and take a look at 4.2. So in 4.2, we are supposed to calculate the velocity of ball Q after the collision. So let's go ahead and take a look at what is happening. So we have a ball P of mass 0.16 kilograms moving east at a speed of 10 meters per second. It collides head-on with another ball Q of mass 0.2 kgs moving west at a speed of 15 meters per second. We can clearly see that from our sketch before the collision. After the collision, ball P moves west at a speed of 5 meters per second, as shown in the diagram below. We can clearly see that. Ignore the effects of friction and the rotational effects of the ball. If the question says that we must ignore the effects of friction, then we have an isolated system. We have a closed system. Momentum is conserved, right? Linear momentum is conserved. So let's take a look at our question. Calculate the velocity of ball Q after the collision. Based on the information we have the mass, the velocities before and after the collision. That leads us to use the conservation of linear momentum. Before the collision, we have two separate bodies. Even after the collision, we have two separate bodies. So this is how our equations are going to look like. The first statement we need to make is that the sum of the momentum before the collision is equal to the sum of the momentum after the collision. So this is the first statement you need to make. Just writing this in the final examination, you will get a mark for just writing this. Obviously, you cannot get this wrong. You just say sum of momentum before is equal to the sum of the momentum after. You will get a mark for just saying this. So after these steps, then we can say, okay, we have two bodies. We have ball P and ball Q. So we're going to have MP multiplied by its initial velocity plus MQ multiplied by its initial velocity being equals to MP multiplied by its final velocity plus MQ multiplied by its final velocity. So there we go. That is the equation we are going to use because we have two separate bodies before and after the collision. Okay, so if you get a mark for this statement, you're not gonna get a mark for this following statement. You only get a mark for one between the two, but I just prefer writing both for the sake of clarity. So we are always going to take direction to the east as positive unless the questions state otherwise. For all the questions you're going to solve, that is going to be the trend. East is positive unless stated otherwise. So the mass of ball P is said to be 0.16 kilograms. So we're going to have 0.16 kilograms multiplied by the initial velocity, which is 10 meters per second, plus the mass of ball Q. It is 0.2 kgs. Its initial velocity is 15 meters per second to the west. So we're going to substitute it with a minus sign because it is to the west and we are taking direction to the east as positive. The mass of ball Q, that is 0.16, and its final velocity is 5 meters per second to the west. So minus sign, minus 5. So now let's move to the mass of ball Q. The mass of ball Q, it is 0.2, and we're interested in the final velocity of ball Q. On the left hand side, we're gonna have minus 1.4 being equals to 0.16 multiplied by minus 5, which will be minus 0.8 being equals to 0.2 VF. So I'm going to take minus 0.8 to the left hand side. So that will be minus 1.4 plus 0.8, which is minus 0.6. So minus 0.6 is equals to 0.2 VF. At this point, we need to divide both sides by 0.2. If we do that, we're going to get minus 3 being equals to VF. Minus 3 is just the direction, which is to the west. So we have 3 meters per second west being equals to VF. So there we go. We have the final velocity of ball Q after the collision. Let's go ahead and do the question that follows. 4.3. Calculate the magnitude of the impulse on ball P during the collision. So we need to focus on ball P, right? Its initial velocity, as you can clearly see here, is 10 meters per second. So we have 10 meters per second. Its final velocity, as we can clearly see, is 5 meters per second. And we know that its mass is equals to 0.16 kilograms. So with this information, we can calculate the impulse. Okay, so the impulse delta P is going to be equals to the mass VF minus VI, right? Momentum final minus momentum initial. We are just taking the mass as a common factor. So the mass is 0.16. The final velocity is 5 meters per second to the west. So that is minus 5. Minus VI, 10 meters per second to the east. So it's just going to be minus 10. So the change in momentum is going to be equals to minus 2.4. This is just equals to 2.4 newtons multiplied by seconds. I'm deciding to use newtons multiplied by second because the question said impulse and not change in momentum. If the question had said change in momentum, I was going to use kg meters per second. But if you use kg meters per second, you will still get your mark. Explain what is meant by an isolated system as used in physics. So an isolated system is a system in which the net external force is 0. That is what we mean by an isolated system. The net external force is 0. That is 4.1. Let's go ahead and take a look at 4.2. So 4.2, the magnitude of the momentum of the bullet before it enters the block is 24 kg meters per second. Calculate the mass of the bullet. Okay, let's go and see what is happening here. So a bullet moves at a velocity of 480 meters per second. It hits a wooden block that is fixed to the floor. The bullet takes 0.01 seconds to move through the stationary block and emerges from the block at a velocity of 80 meters per second east. See the diagram below. Ignore the effects of air resistance and consider the block bullet system as an isolated system. Alright, so again, let's take a look at our equation. The magnitude of the momentum of the bullet before it enters the block is 24 kg meters per second. So we have the momentum, or at least the magnitude of the momentum, being 24 kg meters per second. Calculate the mass of the bullet. So we have the momentum. We want to find the mass of the bullet. This momentum is for the bullet before it enters the block. And we know that before it enters the block, it is moving with a velocity of 480 meters per second. So we have V being equals to 480 meters per second. So obviously with these three variables, we're going to use P is equals to M multiplied by V. This has to be one of the easiest questions I've ever came across, most especially in a final exam. But anyway, stories. Let's go ahead and substitute. P is 24. The mass is what we're interested in. The velocity is 480. So let's go ahead and divide both sides by 480 and see what we end up with. So 24 divided by 480, we're going to have 0.05 kgs, being equals to the mass of the bullet. So there we go. We have our solution to 4.2. Quite an easy question, to be honest. No trickery whatsoever. Let's go ahead and do 4.3. So 4.3, calculate the average net force exerted by the wooden block on the bullet. Okay, so this is paying attention to the bullet. As the bullet strikes the wooden block, it has an initial velocity of 480 meters per second to the east, right? And then when it leaves the block, as it emerges, we have a final velocity of 80 meters per second. This is to the east. So let's take a look. We have VI, we have VF. Obviously, we have the mass of the bullet as we calculated it in 4.2. The mass of the bullet is 0.05, so we're gonna have 0.05 kgs. Another piece of information we have is the time taken for the bullet to move through the stationary block. It takes 0.01 seconds. Here it is on our question statement. So we're gonna have delta t being equals to 0.01 seconds. So there we go. This is the information we have. We want to calculate the average net force exerted by the wooden block on the bullet. This should be easy to do, right? It should be easy for you to see which equation we have to use here. We will use F net is equals to the change in momentum divided by the change in time. So F net will be equals to the mass multiplied by VF minus VI, everything divided by delta T. So the mass is 0.05. If we take direction to the east as positive, VF is 80 minus VI, which is 480, everything divided by 0.01. And if you put that in a calculator, you're gonna get minus 2000, which we know that it is just equals to 2000 newtons to the west, right? Because the negative sign is to the west if we take in east as positive. Momentum is the product of the mass of an object and its velocity. Okay. The second question, 4.2, will the girl roller skate combination move to the left or to the right after the parcel is thrown? Name the law in physics that can be used to explain your choice of direction. So let's go ahead and take a look and see what is happening. Initially, a girl on roller skates is at rest on a smooth horizontal pavement. The girl throws a parcel of mass 8 kgs horizontally to the right at a speed of 4 meters per second. Immediately after the parcel has been thrown, the girl roller skate combination moves at a speed of 0.6 meters per second. Ignore the effects of friction and rotation. We can clearly see the girl on the roller skates and the parcel that is being thrown. So back to our question, will the girl roller skate combination move to the right or to the left after the parcel is thrown? Okay, so let's take a look. The parcel is thrown to the left with a force of a certain magnitude, right? According to Newton's third law, if you apply a force on an object, the object will also apply a force on you of equal magnitude but in the opposite direction. So the girl roller skate combination will move to the right because the girl is applying a force on the box to the left, right? On the parcel, not the box. The girl roller skate combination will move to the left because of Newton's third law. Right, so there we go. That is 4.2. Let's go ahead and take a look at 4.3. So 4.3, the total mass of the roller skates is 2 kilograms. Calculate the mass of the girl. Okay, so let's take a look. We want to find the mass of the girl. We have the mass of the roller skates, obviously. We have the velocity initial of the roller skates and the girl, right? Because before the parcel is thrown, both the parcel, the roller skate, and the girl, they are at rest. The initial velocity is equals to 0, right? That is before the parcel is thrown. So we have our VI, which is equals to 0 before the parcel is thrown, right? So this is before the parcel is thrown. So now let's take a look at what happens after the parcel is thrown. So after the parcel is thrown, the mass of the girl is still unknown. We have the mass of the roller skate, obviously. We also have the mass of the parcel, right? It's 8 kgs. So we have the mass of the parcel, but now we have the final velocity of the girl and roller skates, which is equals to 0.6 meters per second to the left. We know that the roller skate girl combination will move to the left. That's our answer to 4.2. And we also have a final velocity for the parcel. We know that it moves with a velocity of 4 meters per second after being thrown. So with these variables, you can see which equation we're supposed to use, which law we're supposed to use, right? We're supposed to use the conservation of linear momentum. So we can say that the sum of the momentum before the girl throws the parcel should be equal to the sum of the momentum after the girl throws the parcel, right? So let's take a look at the girl and the roller skate first. So let's pay attention to that. Well, the girl and the roller skate, they are one body. We can refer to them as one body, right? I'm saying that because the girl is on roller skates. If the girl is moving with a velocity of 20 meters per second, the roller skates are going to be moving with a velocity of 20 meters per second. So let's take the girl and the roller skates as one body, of which, if we do that, we're going to have mass of girl plus mass of roller skates multiplied by VI plus mass of parcel multiplied by VI, okay, being equals to mass of girl plus mass of roller skates multiplied by VF plus mass of parcel multiplied by VF. So there we go. This is before the girl throws the parcel, and this is after the girl throws the parcel. So let's go ahead and substitute. The mass of the girl is what we are interested in. The mass of the roller skates is 2 kgs. The initial velocity is 0. Plus the mass of the parcel, 8 kgs. The initial velocity is 0. This is before the girl throws the parcel, okay? Being equals to the mass of the girl, what we're interested in, mass of the roller skates, 2 kgs, multiplied by VF, which will be minus 0.6, right? 0.6 meters per second to the left. If we take direction to the right as positive, then that velocity should be negative. Plus the mass of the parcel, 8 kgs, multiplied by its velocity, 4 meters per second. So this is going to give us 0. And we're also going to get 0 from that part also. So we're going to have 0 being equals to the mass of the girl. Let's multiply out here. Let's multiply out. 0 being equals to minus 0.6 mass of the girl plus 2 multiplied by minus 0.6. So that will be minus 1.2. And then plus 8 multiplied by 4. So 8, 16, 32. So we have plus 32. Okay. If we take minus 1.2 and 32 to the left hand side, we're gonna have plus 1.2 minus 32. So we're gonna have minus 30.8 being equals to minus 0.6 mass of the girl. So what is minus 30.8 divided by minus 0.6? We get the mass of the girl being equals to 51.33 kilograms. So there we go. We have the mass of the girl is 51.33 kilograms. Right, let's move to the question that follows. 4.4. So in 4.4, we're supposed to calculate the magnitude of the impulse that the girl roller skate combination is experiencing while the parcel is being thrown. Okay, so the initial velocity is 0, and then after the parcel is thrown, the velocity is minus 0.6. Well, velocity cannot be minus, so let me write 0.6 meters per second. I just need to remember that this is to the left, right? So the mass of the girl and the roller skates, so the mass is equals to 51.33 plus 2, which will give us 53.33 kgs. We want to find the impulse on the girl roller skate combination. So the mass is going to be the mass of the girl plus that of the roller skate, which will give us 53.33. So now we can go ahead and calculate the impulse. The mass multiplied by VF minus VI. The mass is 53.33 multiplied by VF, which is 0.6 to the left, so minus 0.6 minus VI, which is 0. So the impulse is minus 32. We're only interested on the magnitude, so we don't have to stick the direction. Minus 32 kg meters per second. State the principle of conservation of linear momentum. Well, in an isolated or closed system, the total linear momentum is conserved. In an isolated or closed system, the total linear momentum is conserved. So that is the answer to 4.1. We just have to state the principle of conservation of linear momentum. Let's go ahead and take a look at 4.2. So in 4.2, we're supposed to calculate the magnitude of the velocity of trolley Y immediately after the collision. So let's go ahead and take a look at our question statement and figure out what is going on. So we have a trolley X of mass 1.2 kilograms that travels at 8 meters per second east and collides with trolley Y of mass 0.5, which is initially at rest. So we know that its initial velocity is equals to 0. That's what at rest implies in physics. Okay, let's carry on. Ignore all frictional effects. So if the question statement says we must ignore all frictional effects, it means that we have a closed system. Momentum is conserved. So you need to always check that in your question statement. Does it say you can ignore the effects of friction? If it says so, then momentum is conserved. Let's carry on. The velocity time graph below shows the velocity of trolley X before, during, and after the collision with trolley Y. Okay, so like we have read on our question statement, the initial velocity, the velocity of trolley X before the collision is 8 meters per second. So right here is before the collision at 8 meters per second. Okay, and then this will be after the collision. So this is VI, which is 8 meters per second, and this is VF, which is 4 meters per second for trolley X. Okay, so let's go ahead and calculate the magnitude of the velocity of trolley Y. How are we going to do that? We'll start by saying that because we are told we can ignore the effects of friction, momentum is conserved. That tells us that the sum of the momentum before the collision will be equals to the sum of the momentum after the collision. Okay, we have two trolleys, X and Y, right? So initially, before the collision, we're gonna have M1 V initial plus M2 V initial being equals to the sum of the momentum after the collision. So they don't stick together after the collision, right? There is nowhere in the question where that is mentioned. So after the collision, we will have M1 V final plus M2 V final. Okay, so there is a mark for this statement. The sum of the momentum before is equal to the sum of the momentum after. So let's go ahead and start with trolley X. Trolley X, before the collision, the mass is 1.2. The initial velocity is 8 meters per second to the east. Let's take direction to the east as positive. So we're going to have 1.2 multiplied by 8 plus M2, the mass of trolley Y. This is 0.5. Before the collision, it's at rest, so the velocity is 0. This is equals to M1, 1.2, and after the collision, the velocity of trolley X is 4 meters per second. So we have 4 right here. And then plus M2, the mass is 0.5, and we want to find VF. So what is 1.2 multiplied by 8? We have 9.6 being equals to 1.2 multiplied by 4, because 0.5 multiplied by 0 will give us 0. So now we are doing 1.2 multiplied by 4, which is going to give us 4.8 plus 0.5 VF. So we have to take 4.8 to the left hand side. We're going to have 9.6 minus 4.8 being equals to 0.5 VF. So 9.6 minus 4.8, that is 4.8, which is equals to 0.5 VF. We can take, we can divide both sides by 0.5. We're going to have 9.6 meters per second being equals to VF. So there we go. This is the final velocity of trolley Y immediately after the collision. So there is a mark for this step and a mark for this step, making a total of 4 marks. So, ladies and gentlemen, this is how we apply the conservation of linear momentum. This is how we do it. Let's move to the question that follows. So 4.3, the question says, calculate the magnitude of the average net force that trolley X exerts on trolley Y during the collision. So we are interested on trolley Y, right? We want to determine the magnitude of the average net force that trolley X exerts on trolley Y. So let's go ahead and pay our attention to trolley Y. With regards to trolley Y, the initial velocity, it starts at rest. So Vi is equals to 0. And its initial velocity, that of trolley Y, what we just calculated, 9.6. So its final velocity is 9.6, like we just calculated. And then its mass is equals to 0.5. We're just trying to gather all the information we have so that we can be able to choose a formula. We don't choose a formula and force the information. No. The information guides us to the formula we need to use. So there we go. We have the initial velocity, the final velocity, and the mass. We are interested in the force, right? So it seems like we can use F net is equal to the change in momentum divided by the change in time. This is because the change in momentum is just mass, Vf minus Vi, everything divided by delta T. So we want to use this equation. Do we have the mass? Yes, we do. Do we have Vf? Yes. Vi? Yes. Do we have delta T? We do have delta T, but it's not obvious that we do. But if you take a look at the velocity time graph we're given for trolley X, you will realize that this is where the collision starts at Vi, and this is where it ends at Vf. And we have the corresponding time. They collide at 20.1 seconds, and at 20.2, that's where the collision comes to an end. So we can have the mass of the object being equals to 0.5. Vf is 9.6. Vi is 0. And the change in time final is 20.2, right? And the time initial is 20.1. If you put this in your calculator, you're gonna get 48 newtons. This is the magnitude of the average net force that trolley X exerts on trolley Y. There we go. Let's move to the question that follows. 4.4. Is the collision elastic or inelastic? Explain the answer by means of a suitable calculations. Right. All the subtopics we have covered are all coming together now. We are interested on whether a collision is elastic or inelastic. So let's go ahead and take a look at how that will look like. Before we answer this question, the first thing we want to do is to say that EK is equals to a half mv squared. This is just the equation for kinetic energy. You want to write that equation down. As soon as you write that equation down, you have a mark, right? And then after that, you can then determine whether the collision is elastic or inelastic. So how do you determine that? You calculate the sum of the kinetic energy before the collision and see if it is equal to the sum of the kinetic energy after the collision. So when we were talking about collisions, we say that for a collision to be elastic, momentum needs to be conserved and kinetic energy needs to be conserved. But we know that there's no frictional force in our system. So momentum is already conserved. We know that, okay? We used that fact to answer 4.2. Now, we just need to check the kinetic energy. Is the kinetic energy conserved? So let's go ahead and find out. If I start with trolley X, before the collision, we're going to have a half. The mass is 1.2. The initial velocity is 8 meters per second squared, right? And then plus a half. This is for trolley Y now. The mass is 0.5. Initially, it's at rest. So we're going to have 0 squared. This is equals to, we get 38.4 joules. The SI unit of energy is joules. So this is the kinetic energy before the collision. Let's go ahead and take a look at the kinetic energy after the collision. We're going to have a half concentrating on trolley X first. The mass is still 1.2. The velocity is 4 meters per second. We square that plus the kinetic energy of trolley Y. The mass is 0.5 and the velocity after the collide, which we calculated in 4.2, is 9.6, and we square that. If you put that in your calculator, you're gonna have 32.64 joules. So there we go. We have EK before and after the collision. So we can go ahead and conclude and say that the collision is inelastic, right? And why do we say so? EK before is not equals to EK after, right? If this is the case, then our collision is inelastic. It would be elastic if EK before is equals to EK after. So there we go. This is how we determine whether a collision is elastic or inelastic. Momentum and impulse topic test. Let's take a look and see what is going on. So, question 1, multiple choice questions. Let's see how we approach this kind of questions. 1.1, which one of the following best describes an inelastic collision? So, before we even look at our options A, B, C, and D, we know that a collision is deemed inelastic when momentum is conserved but kinetic energy is not. So that's what we are looking for essentially in our options A, B, C, and D. Option A, both momentum and kinetic energy are conserved. That would be an elastic collision, not an inelastic collision. So A cannot be our answer. B, total kinetic energy is not conserved, but total linear momentum is conserved. We need to look no further. The correct answer to 1.1 is B. 1.2, in the equation F net multiplied by delta T is equals to delta P, the product of F net delta T represents the impulse, right? We know that from theory. There's nothing we are calculating here. There's nothing we need to figure out. We're just taking our answer as it is. So 1.2, the answer is C. F net delta T is the impulse. There's really no need for an explanation here because that is just theory, okay? But things get interesting when we go to 1.3 and 1.4. Take a look at 1.3. So a body is moving at a constant velocity and has kinetic energy E and momentum P. The velocity of the object is doubled. Which one of the following correctly gives the magnitudes of both the kinetic energy and momentum? Right, so it has the velocity v initially, and it is then changed to 2v. So the momentum when the velocity is v will be p is equals to mv. And then the kinetic energy when the velocity is v will be a half mv squared. Let's take a look at the scenario where the velocity is now 2v. The momentum will be p is equals to, let me say, px, right? Px will be equals to m multiplied by 2v, which is equals to 2mv. So this is 2p. So the momentum doubles when the velocity doubles. Now let's take a look at kx. We're gonna have a half m instead of v. We have 2v, and we square that. This is gonna be equals to a half m multiplied by 4v squared. This is equals to 4, right, multiplied by a half mv squared. We know fully well that a half mv squared is just k. So kx, the new kinetic energy, is 4 times the initial, and the momentum is 2 times the initial. So which option gives us that? So option A, we have 2e, 2p. Our answer is option C, where we have 4e, and 2p. So the answer to 1.3 is C. So there we go. This is how we solve these kind of questions. We're going to use the same technique or something close in 1.4. So 1.4 says a ball of mass m strikes a wall perpendicularly at a speed 2v. Immediately after the collision, the ball moves in the opposite direction at a speed v, as shown in the diagram below. The magnitude of the impulse of the ball is. So impulse is equals to the change in momentum, right? But it is also equals to F naught delta t. So we're going to have m Vf minus Vi. So m is just m, and then let's talk about v. It strikes the wall with a velocity of 2v, and then it leaves the wall with a velocity of v. But if you look at the direction, this is to the right and that is to the left. So we need to think about that when we substitute. So which direction do we need to take to the do we need to take as positive, and which direction is going to be negative here? If we take direction to the right as positive, we'd have 2v minus v, which will be plus, right? So this is going to give us 3mv, which is option D. That is 1.4. We need to be comfortable with working with variables. Okay. Question 2. Let's take a look. The diagram below shows a 65.4 kg dancer who jumped in the air and landed a foot on the floor at 7 meters per second. She came to a complete stop in 0.5 seconds. Right, let's take a look. 2.1. Define the term impulse in words. Well, I'm gonna let you do that. And then 2.2, let's take a look at 2.2.1. We are supposed to calculate the impulse of the dancer. So F net multiplied by delta t, not delta p, but delta t, as I'm saying, is equals to delta p. Delta p is the impulse, but it is also equals to the change in momentum, right? So we have our initial velocity and we have our final velocity, right? We just need to decide on which direction we are taking as positive, right? If we take upwards as positive, we're going to have the mass of the dancer being 65.4. Let me just verify. Right. And then the final velocity, the dancer comes to a complete stop in 0.5 seconds. So the final velocity is 0 minus the initial velocity. We are taking up as positive. So we're going to have minus 7. So if you put that in your calculator, we are going to get 457.8 newtons multiplied by seconds. Right. If the question had said change in momentum, it would be kg meters per second. But because we are looking for the impulse, newtons per second. Not newtons per second, but newtons multiplied by seconds. Right. 2.2.1. 2.2.2 on the other hand, the magnitude of the force which the floor exerts on the dancer's foot. So take a look at this. We are looking for the force, right? We have calculated delta P and we have delta T. Seems quite straightforward. So F net will be equals to the change in momentum, the impulse, divided by delta T. So we already have delta P, which is 457.8 divided by the change in time, which is 0.5 seconds. So we have 0.5 seconds, right? And when I put that in my calculator, I'm getting a 915.6. Since our answer is positive, this will be upward, right? Because we're taking upward as positive. Okay, 2.2.2. Let's take a look at 2.3. Right, 2.3 is quite an interesting question. In the diagram below, a 600 grams football, which is initially at rest, is thrown at the wall. The following graph shows the change in the applied net force over a period of time. We can clearly see there the graph forms a triangle. And then 2.3.1, we're supposed to state Newton's second law. in terms of momentum. Right, so what does it say in terms of momentum? Take a look at this. F net is equals to ma, that is terms of acceleration. In terms of momentum, we have F net being equals to delta p over delta t. So how do we then state Newton's second law in terms of momentum? The net force acting on an object is equals to the rate of change in its momentum. There we go. That is Newton's second law in terms of momentum. And then 2.3.2, calculate the magnitude of the impulse exerted to the football. Okay, so take a look at this once more. The impulse F net delta t is equals to delta p. So what is the impulse? F net multiplied by delta t. If you take a look at our graph, we just need to calculate the area of the triangle in order to have our impulse. Right, the area of the triangle there will give us the impulse, because in order to calculate the area, we are saying half base multiplied by the height, of which we have F net and delta t. Okay, so let's go ahead and do that. Delta p is going to be equal to half base multiplied by height. So delta p is going to be equal to a half the base time taken from 0 to 12 seconds. So that is 12. And then the height from, let me just take out my ruler. Right, this is our height. This is our height. So we needed to go to a graph and see where it cuts on the y-axis. So let's take a look. This is 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. Right. So you can clearly see that it cuts at 34. So we have 34 right there. And then now it's just a matter of putting that in our calculators and see what we have. So let me just do that. I'm getting 204 newtons multiplied by seconds above said. Right, that is 2.3.2. 2.3.3 says that use the calculation to show that the velocity at which the ball or at which the football hits the wall is 340 meters per second. The velocity at which it hits the wall is 340 meters per second. Right, so let's see what we have. We have delta p, right? We calculated it using the area of the graph, but delta p is also equals to m vf minus vi. So we can use this in order to find the velocity. We are using what we're given to find that which we don't have, that which the question is asking us to find. So delta p, that is 204. The mass of the ball is 600 grams, so that is 0.6 kgs. And then the final velocity is what we are interested in, right? Minus the initial velocity. The ball comes from rest, so this is 0. Okay, so it's just a matter of dividing both sides by 0.6 in order to find VF. So VF is equals to 204 divided by 0.6. This is 340 meters per second. Somewhere close to the speed of sound in air. But anyway, stories. Let's take a look at question 3. Right, so question 3, in the diagram below, a trolley of mass 5 kgs moves at 4 meters per second east across a frictionless horizontal surface. So we don't have any friction there. A box of mass 1.5 kg is dropped onto the trolley. Then the trolley and the box continue to move in the same eastward direction. Take eastward direction as positive. 3.1, I'm going to let you state the law of conservation of linear momentum. And then 3.2.1, we're supposed to calculate the velocity of the trolley box system after the box is dropped onto the trolley. Right. So usually in physics, if 3.1 says state the law of conservation of linear momentum, and 3.2 you're supposed to calculate something, that's something which you're supposed to calculate, you are most likely to use the law that you've stated. So if we use the conservation of linear momentum here, we're going to say that the momentum before is equals to, well, not the momentum, but the sum of the momentum before is equals to sum of the momentum after, right? After the brick, is it a brick? After the box has been dropped down to the trolley, not a brick, right? So we have M1 V1, that is the momentum of the box, M2 V2, that is the momentum of the trolley. And then after the box falls onto the trolley, right, after it is dropped onto the trolley, we're gonna have M1 plus M2 multiplied by VF, because they now move as one unit. So the box as it is being dropped onto the trolley will have a mass of 1.5, but its velocity along the x-axis is 0, right? Plus mass of the trolley, which is 5. Its velocity, it says 4 meters per second to the east. We're already told that we must take direction to the east as positive. So that is 5 multiplied by 4. Okay. After the collision, we have 1.5 plus 5 multiplied by VF. So obviously this will give us 20, and this is equals to 6.5 VF. So VF is equals to 3.08 meters per second east. So there we go, 3.2.1. 3.2.2, we want to calculate the change in momentum of the trolley. So change in momentum, M VF minus VI. Initially is, oh well, not initially, because the mass is always conserved, it's the same as the mass is 5, but the final velocity is 3.08. The final velocity is 3.08. And then what about the initial velocity? It is 4 meters per second in the same direction. So the change in momentum therefore is 4.62 kg meters per second. Do you see the difference? When I'm talking about impulse, I use newtons multiplied by seconds. When I'm talking about change in momentum, I use kg meters per second. That's how it's supposed to be done. Right, 3.3. State the condition for an elastic collision. Right, we've already talked about that as we were answering the MCQ. For a collision to be elastic, momentum needs to be conserved, kinetic energy needs to be conserved. And then 3.4 is saying that use a calculator to show that the collision between the box and the trolley is elastic or inelastic. So take a look at this. We don't have to show that momentum is conserved anymore. We actually don't have to do that. Why? We were told in the question statement that the trolley is moving on a frictionless horizontal surface, right? If it is moving on a frictionless horizontal surface, the linear momentum is conserved. That is why we use that theorem in 3.2.1, because how are we using that theorem if the linear momentum is not conserved, right? So already the linear momentum is conserved. We just need to check the kinetic energy, whether it is conserved or not, right? But we cannot start by saying EK before is equals to EK after. The question cannot say show that x is equals to 2 and then you start by saying x is equals to 2, therefore blah 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 blah. Doesn't make any sense. So right, we need to calculate EK before separately, calculate EK after separately, and see if they're equal to each other. So let's do that. EK before, right, the sum. So we're gonna have half mv squared for the box plus half mv squared for the trolley. So for the box, half m is 1.5, it's v is 0 along the x-axis, and then half the mass is 5 for the trolley, the velocity is 4, and we square that. Right, so let me just put that in my calculator and see what I have. This is 40 joules. And now let's calculate EK after the collision. Right, so after the collision, they move as one unit, right? So we are going to have a half 5 plus 1.5 multiplied by 3.08 squared, because after the collision they move as 1 unit. So let me just calculate that and see what happens. I'm getting 30.83 joules. So clearly EK before is not equals to EK after. So we can confidently say that the collision is inelastic. Right, let's move to the following question. Question 4. The diagram below shows shows car A of mass 800 kgs traveling slowly near the traffic light. Car A is hit from behind by car B of mass 950 kgs traveling at 10 meters per second in an eastward direction. I found myself in one of these situations, so it's going to be quite fun calculating, knowing that I've been in such a situation. Right, the change in momentum with time of car A just before and after the collision is represented on the diagram below. Consider the system to be isolated, so momentum should be conserved. 4.1, we're supposed to define momentum. I'll let you guys do that, and then let's take a look at 4.2. Use the information in the graph and the relevant equation to explain why the net force acting on car A is 0 between T10 and T20. Right, the net force between T10 and T20 is 0. The question is saying let's use a relevant equation to explain why. Okay, so between T10 and T0, we can see that the momentum is constant, right? And we know that F net is not only equals to ma, but F net is also equals to delta p over delta t. So the momentum is constant. So what is the change in the momentum if the momentum is constant? The change in the momentum is 0. So we have 0 divided by delta t. So this is going to give us a 0 newtons. So that's how we can easily show that the net force should be 0 between T10 and T20, because the momentum is constant. It is not changing. Right. 4.3. Use the information in the graph to calculate the magnitude of the velocity of car A just before the collision. Well, it's equation, honestly. Just before the collision, the magnitude of, okay, yeah, so just before the collision is at that point, right, before the momentum starts changing. So the magnitude of the velocity, P is equals to M multiplied by V. The momentum is 20,000, is given in the equation, in the graph. And then what is the mass of car A? It is 800 kgs. So we have 800 multiplied by the velocity. So V is equals to, let's see, 25 meters per second. So there we go. That is 4.3. It says the magnitude, so we don't have to worry about the direction. And then 4.3.2, that is 4.3.1. The velocity of car B just after the collision. 4 marks. Okay. B after the collision. Do we need to do some complicated things there? So before the collision, car B, let me see. I'm trying to see if car B is stationary. Right, the diagram below shows car A of mass 800 kg traveling slowly near the traffic light. Car A is hit from behind by car B. Right, car A is hit from behind by car B. Okay, so both these vehicles are moving before the collision. Right, the sum of the momentum before will be equal to the sum of the momentum after. Obviously, I'm able to use that because we are told that our system is isolated, right? So before the collision, this is the graph for car A, right? So before the collision, the momentum of car A is 20,000 before the collision, plus the momentum of car B, which is going to be 950 multiplied by 10. It's here in the equation, right? Car B is moving at a velocity of 10 meters per second in the eastward direction at a speed, right? And this is going to be close to the momentum after. The momentum after of car A is 10,000. Can clearly see that from the graph. It's 10,000. And then plus that of car B after the collision. So 950 multiplied by V. Okay, so now time to press my calculator. So I have 20,000 plus 950 multiplied by 10. This is 29,500, and then this is equals to 10,000, right? 10,000 plus 950 V. So obviously if we take 10,000 to the other side, we're just going to have 19,500, and this is equals to 950 V. Dividing 900 by 950 on both sides, we get the V final being 20, what am I writing there? Being 20.53 meters per second. So there we go, to the east. We have clearly taken the direction to the east as positive here. I hope you're not one of those people that just memorize definitions without knowing exactly what they mean. So here in question 4, the only question I would understand if you got it wrong is 4.5. That is the only question that I think was a bit difficult. Everything else is just basic stuff. So let's go ahead and look at 4.1. We're supposed to define the term impulse. Let me show you something. We know fully well that F net is equals to the change in momentum divided by the change in time. If we cross multiply, the change in momentum or the impulse is equals to F net multiplied by delta t. So what is the definition of impulse? If you look at this formula, the impulse should be the product of the net force and the time it acts on the object from the formula. That's the connection you need to make between definitions and formulas. That is 4.1. Let's go ahead and take a look at 4.2. Use the information on the graph to determine the magnitude of the impulse as the ball hits and bounces off the force sensor. Right, let's go through our question statement and see what is going on. When a ball hits and bounces off a surface, it exerts a force on that surface. Grade 12 learners investigated how this force varies over time as the ball hits a force sensor and bounces off. A 50-gram soft ball was dropped from a height of 1.5 meters vertically above a force sensor connected to a laptop as shown on the diagram. And the graph we're given the force versus the time. The force is in Newton and the time it is in milliseconds. So as soon as you don't realize that the time is in milliseconds, you're probably going to get the question wrong. Let's use the information in the graph to determine the magnitude of the impulse. So the impulse is the force multiplied by the time. We have a shape, we have a triangle. So in order to find the impulse, we need to find the area of this triangle. How can we find the area of a triangle? That is half base multiplied by height. So this will be equals to a half base. Our base is the time in milliseconds. We go from 0 to 15 milliseconds. So we're going to have 15 divided by 1000. Multiplying by 10 to the minus 3 is the same as dividing by 1000. Now we have converted our time from milliseconds to seconds. Multiply by our height. Our height is right here. We are given the value as 64.13. So we have 64.13. That is the impulse, half base times height. If you put that in your calculator, you'll get 0.481 newtons multiplied by seconds. That is 4.2, calculating the impulse. 4.3, state the magnitude and the direction of the change in the momentum of the ball. The impulse is equal to the change in the momentum of the ball. So we already have our answer. We just need to quote it. Right, we need to state the magnitude and the direction. So the magnitude is 0.481 kg meters per second. Why am I using kg meters per second? Because when you are calculating the change in momentum, you use the mass and the velocity. So that's why I have kg meters per second. But when you calculate in impulse, you have newtons multiplied by second. That is the only difference. Right. So we have 0.481 as the magnitude. What about the direction? The ball is being dropped and it hit the force sensor. when it hits the force sensor will apply a force on the ball upwards. So the impulse will be upwards. So this is the direction we need to indicate here, that it is 0.481 upwards. So in 4.4, if the velocity of the ball just before it hits the force is 5.42, so VI is equals to 5.42 meters per second downwards. Calculate the velocity with which the ball will bounce off the sensor. So we're looking for VF. What is VF? That's what we're interested in. We need the mass of our soft ball. The mass is equals to 50 grams, which we're going to divide by 1000 to convert to kgs. And what else do we have? We have the impulse. Delta P is equals to 0.481 upwards. So VI is downwards. We can substitute it with a negative sign because it is downwards. And then the impulse is upwards. So we're going to substitute it with a positive sign. That's if we take up as positive. You can take down as negative, and you can take down as positive and do it the other way around. Anyway, stories. So F net multiplied by the time is equals to the change in momentum. So what is F net multiplied by the time? That is 0.481. This is equals to the change in momentum. The mass multiplied by VF minus VI. So we're going to have 0.481 being equals to 50 divided by 1000 multiplied by VF. VF is what we're interested in. Minus 5.42. The first thing we should be doing here is dividing both sides by 50 divided by 1000. If we do that, we're going to get 9.62 being equals to VF plus 5.42. Now we just need to take 5.42 to the left hand side. We're going to get VF being equals to 4.2 meters per second upwards. That is our final velocity. 4.5, the only question that was a bit tricky. Everything else is just the basic stuff. So let's go ahead and take a look at 4.5. The ball is now replaced with a harder ball of the same size and mass. Will the force on the force sensor increase, decrease, or remain the same? The force is going to increase. Let me show you why. We know that F net is equals to the change in momentum divided by the change in time. If instead of using a softer ball, you use a harder ball, delta T is going to decrease. The time of contact is going to decrease. So if the time of contact decreases and the change in momentum stays the same, then it is easy to see that F net is going to increase. F net is inversely proportional to the time of contact. So the answer to 4.5 is increases. Write down the horizontal speed of the brake just before the girl catches it. So here on the question statement, we are told that the girl, she catches a brake of mass 5 kg, which is thrown vertically downwards from the top of a high wall. So the brake is thrown vertically downwards from the top of a high wall, right? So if a brake is thrown vertically downwards, then it has a horizontal speed of 0 meters per second, right? Because it's only moving along the horizontal. So the answer for 4.1, we're going to have Vx, x being for horizontal, being equals to 0 meters per second. And then now moving to the next question, 4.2. 4.2 is saying that let's calculate the girl's speed just before she catches the brake. Let's calculate the girl's speed just before she catches the brake. So let's go through the question statement and have an idea of what is going on. So we are told here that a girl on roller skates of combined mass 52 kg moves horizontally at a certain constant velocity. So we have some mass which is equals to 52 kgs, and then the velocity is unknown, right? And then goes on to say that she catches a brake of mass 5 kg. So we have a mass of the brake which is equals to 5 kg. it's been thrown vertically downwards, so it has a horizontal velocity of 0, like we've deduced in 4.1, and then the girl continues to move in a straight line at a speed of 2.4 meters per second after catching the brick. So when we have the girl of mass 52 kgs plus the brick of 5 kgs, they move together at a velocity of 2.4 meters per second, right? Which law are we going to use to solve this problem? We're going to use the conservation of linear momentum, right? So that is to say that the momentum before, the sum of the momentum before will be equals to the sum of the momentum after. So let's go ahead and try calculate the momentum before. So before, we have a mass of the girl, right? And then it's moving at a certain velocity, and that will be the momentum of the girl, plus the mass of the brick. It's moving at a certain velocity, and then that will be the momentum of the brick. And then after the girl catches the brick, we now have m1 plus m2, right? The mass of the girl and the brick, and then they're moving at the same velocity, right? So what is the mass of the girl? We know fully well that the mass of the girl is 52 kgs. And then the velocity initially before catching the brick, it's unknown. It's what we're looking for. And then plus the mass of the brick, which is 5 kgs, and then multiply by the velocity of the brick before the girl catches it. We're interested in the x component, so we're going to have 0 here, and then this will be equals to obviously the mass of the girl plus the mass of the brick, that will be 52 plus 5 multiplied by the velocity at which they're moving at. So we have multiplied by 2.4. So 5 multiplied by 0 is going to be 0, right? So we're going to just be left with 52 multiplied by the velocity of the girl before catching the brick. So if we solve for that, right, we're gonna get a velocity being equals to 52 plus 5 multiplied by 2.4. And then everything divided by, we divided by 52, the coefficient of V. And then the answer here is 2.6308 meters per second to the direction the girl was initially moving at, right? Yeah, this question doesn't really say a lot about the direction, whether the girl is moving to the east or the girl is moving to the right. But since the question says speed, we can just forget about the direction and just write the magnitude, right? And then now let's move to 4.3. So what do we have here on 4.3? The girl brick combination moving at 2.4 meters per second moves on to a rough surface. She comes to rest after moving 2 meters along the rough surface. And then 4.3 is saying that let's write down a pair of action reaction forces acting while the girl catches the brick. So when the girl catches the brick is going to apply a force on the girl, right? So we're going to have the weight of the brick, and then a force opposing the weight of the brick. That will be the normal force of the girl's hands, right? Because the brick is going to lay on the girl's hands. The reason why the brick doesn't go and hit the ground, it is because the girl is holding the brick and exerting a normal force, because we know that if you put an object on top of another, then there's going to be a normal force. So we have a normal force there exerted by the girl's hands, right? And then another pair, we can start with Fg, the force of gravity, right? The force that the earth is pulling the girl with. We know fully well if the earth is pulling the girl, then the girl is also pulling the earth. So we have that force there. And then those are our action reaction pairs. And then now moving to 4.4. So let's solve 4.4, right? The question is saying that let's calculate the magnitude of the net force exerted by the rough surface to bring the girl brick combination to a stop after 2 meters. So let's look at the information that we have and see what we can do, right? So we know that after the girl catches the brick, they start off at an initial velocity of 2.4 meters per second. And then they come to a complete stop. So we have VF being equals to 0 meters per second. And then what else do we have? We have the mass of the girl brick system. So that will be 57 kgs, right? And then we're looking for Fnet, right? So based on the variables we have here, you can easily see that Fnet, we can find it using Newton's second law in terms of momentum, right? So we have delta P divided by delta T, right? So Fnet is equals to, so what is delta P? The mass multiplied by VF minus VI, right? So we have VF minus VI divided by delta T. So let's just go ahead and substitute and find our answer real quick. So the mass will be 57 kgs. VF is 0, they come to a complete stop, and then VI is 2.4, and then divided by delta T. Right, now we have a problem. We need delta T and we don't have it. So how can you calculate that? Let's look at the variables we have again. We have VF, we have VI, and then apart from that we have delta X, right? And then we're looking for delta T. So which formula can we use to find delta T? It should be easy to see that we can say that delta X is equals to VF plus VI divided by 2 multiplied by delta T, right? Yeah, very rarely do we use this formula, but then yeah, look at us now, we have to sort of use it. So delta X is 2, VF 0, VI 2.4 divided by 2 multiplied by delta T, right? So we divide both sides by the coefficient of delta T. So delta T, so we have delta T is going to be equals to what? 2 divided by 2.4 divided by 2. So our delta T is 1.6667 seconds, right? So now we can substitute this delta T on the equation we had, right? So if we do that, we're gonna have Fnet. So we have Fnet being equals to, so 57, and then 0 minus 2.4 divided by delta T, which we now know is 1.6667. And then if you put that in your calculator, we shall get minus 82.0784, right? So we can just say 82.0784 newtons. And then we don't have to think about the direction because the equation said the magnitude. Let's just leave it like that. Question 4 says a simple rocket system consists of 2 parts. A of mass 3m. So let me jot that down. So we have A, and then they're saying that the mass is 3m kg or some unit, and then B of mass 2m. So we have B, which is mass of 2m kg or some unit. I'm not so sure. As shown in the diagram, below, B is stacked on top of A, and if you look on the left hand side, there it is. Before the collision, B is on top of A, and then after the collision, A is going down, and then B keeps on going up, I'm assuming. 4.1 says state the principle of conservation of momentum in words. That is just the total linear momentum in an isolated system is conserved, right? The sum of momentum before is equals to the sum of momentum after in an isolated system. And then 4.2 says the rocket is traveling vertically upward at a constant speed v. So let me write that down. A, when it's with B, their velocity, let me write that down. Their velocity is 1 divided by 3 v. No, it's actually, the velocity is v, I'm sorry. When an internal explosion causes A to move downwards at a
speed 1 divided by 3v. So there's a explosion, an internal explosion, and now A is moving downwards at v equals to 1 divided by 3v, right? And then for B, we don't know what is going on. And then the question says, okay, ignore all external forces on the rocket. The question now says, calculate the velocity of B in terms of V immediately after the internal explosion. So this is our scenario. Let me get it. This is our scenario before the explosion, and then this is what we have after the explosion. So this momentum here before is supposed to be equals to this momentum here after. That's what the conservation of momentum states, that the sum of the momentum before is equals to the sum of the momentum after, if the system is isolated or is closed. And then the question says, ignore all the forces on the rocket. So that tells us that the system is closed. Okay, so before the masses are together, right? So that will be m of body A plus m of body B, and then they're traveling at the same velocity. That's what the question states. And then after they're saying that A goes down, so we'll have m A, the mass of A, and then the velocity of A, which we're given. Now that they've exploded, they're no longer together, so the masses are apart. So we're gonna have the mass of B and then the velocity of B. The mass of A is said to be 3m, so we're gonna put 3m plus the mass of B, which is 2m, and then the velocity is just given as v, so that's exactly what we're going to have. The mass of A, we've already said that is 3m, and then the velocity of m is 1 over 3v. But then I want you to realize that A is going down, and common sense says we always take up as positive. If you take down as positive, that's fine, but then to me it doesn't make sense. Up is positive. So because A is going down, instead of 1 over 3v, I'm going to put minus 1 over 3v, right? Minus 1 over 3v plus m of B is 2 meters. So, it's 2m, I'm sorry. So we're going to have 2m multiplied by the velocity which we are interested in. So that's what we are supposed to find. So 3m plus 2m will give you 5m, then multiply by v, that's 5mv, right? That's our left hand side of the equation. Then 3m multiplied by minus 1 over 3v, that will give you minus 1v, right? So, minus 1mv, right? Because this 3 here on the denominator is gonna cancel out with this 3. And then plus 2 v. Let's denote this as v of b, so that we don't confuse our variable v with the v of b we're trying to determine. So the next step is to take this term here to the left hand side, so that we can isolate v of b. So we're gonna have, when it goes to the other side, it's gonna change its sign, obviously. So we're gonna have 6 m v equals to 2m v of b. We divide both sides by 2m, so that we can isolate v of b. Divide by 2m. Yeah, we're gonna be left with 3 here, because 6 divided by 2 is 3, right? So this will imply that v of the body B is equals to 3v. The question says we must find it in terms of v, so that is what we're going to find. So it's 3v upwards because we're taking up as positive. That's how we do the problem. It's not really complicated, apart from the fact that now we have a vertical. We're working on the vertical, and usually on momentum and impulse, you're working on the horizontal. But then apart from that, it's just straightforward. The masses are joined initially, and then after that they're separated. So for EP before, you're going to add the masses and have one velocity, and then for EP after, you're going to have the separate masses with the different velocities. Yes, I think I should do a separate introductory video on momentum and impulse. So you can let me know in the comment if that's something you'd be interested in. So if we move ahead, we have 4.3, which says the graph below shows the average force exerted by A on B during the internal explosion as a function of time. And then there we have it. On the y-axis we have average force, and then on the x-axis we have time. The question says, name the physical quantity represented by the area under the graph. So to calculate the area under the graph, you have to multiply the length by the breadth, right? Assuming that the length is going up, then it means you're gonna have force, the average force. So force average multiply by the time, right? But then the time doesn't start at 0, so it's basically delta t, because you have some time initial and some time final. And then which quantity is given by f average multiplied by delta t? That is delta p, right? So the physical quantity represented by the area under the graph is impulse, change in momentum. So that is coming from the formula. So this is what the question is asking for, right? So that is coming from the formula F net equals to delta P divided by delta T. So let's move ahead. 4.4, it says redraw the graph in your answer book on the same set of axes. Sketch the graph on the average. Sketch the graph of the average force that B exists on A as a function of time. So let me just put in an axis there. So that's our Y, that's our X, and then so we have force average, and then we have time in seconds, right? And then that's F A on B, right? The question says find FB on A. Newton's third law says that if body A exerts a force on body B will exert a force on body A of equal magnitude, but then in the opposite direction. So because this graph is on top of the x-axis, we're just supposed to draw the same thing, but then below the x-axis, so that the force has a negative sign, right? Equal magnitude, but opposite direction. So these two are supposed to be equal, this part and this part. And that's it for this question. If you like the video, please subscribe. Trolley X of mass 1.2 kgs travels at 8 meters per second east and collides with trolley Y of mass 0.5 kg, which is initially at rest. And then the velocity time graph below shows the velocity of the trolley X before, during, and after the collision with trolley Y. And then we have a fancy sketch there. And then the first question, 4.1, which is
saying let's state the principle of conservation of linear momentum. We'll leave that for you. And 4.2.1. So for 4.2.1, we're looking for the velocity of trolley Y immediately after the collision. So how can we possibly determine the velocity of trolley Y immediately after the collision? We are going to use the principle of conservation of linear momentum, because we know fully well that the sum of the momentum before a collision should be equal to the sum of the momentum after a collision, right? So what is the momentum before a collision? We're going to have the momentum of trolley X plus the momentum of trolley Y, and then after the collision we're going to have the sum of momentum of trolley X plus the sum of the momentum of trolley Y, right? So if we calculate the sum of the momentum of trolley X, let's not forget that P is equals to M multiplied by V, right? We're going to have 1.2 multiplied by 8. So now we can see that we need to decide on a direction. So let's take direction to the east as positive, right? And then the trolley, the momentum of trolley Y, it is at rest, right? So we have 0.5 multiplied by 0, right? This will be equals to the momentum after the collision of X. We have 1.2 multiplied by the velocity. The velocity is on the graph, right? Because here, this is the velocity before the collision, during the collision, and then immediately after the collision. So we have 4 then, and then plus 0.5 multiplied by the velocity of trolley Y, right? So without wasting any time here, we're gonna say that the velocity of trolley Y should be equals to, so we have this 1.2 multiplied by 8 there, so we're gonna have 1.2 multiplied by 8, and then this, because we're multiplying by 0, is gonna fall apart, right? And then minus this here, which is just 1.2 multiplied by 4, and then everything divided by the coefficient of Vy, which is 0.5. So if we put that in our calculators, we shall get Vy is equals to 9.6, right? We take in direction to the east is positive, so this will be 9.6 meters per second to the east, right? To the east. And now let's do 4.2.2. So 4.2.2 is saying that let's find the average net force that trolley X exerts on trolley Y during the collision. The average net force that trolley X exerts on trolley Y during the collision. We already know that after the collision, trolley Y is going to move to the east, right? So the direction of this net force should also be to the east, right? Irregardless of the sign we're going to get in our calculation, right? Because the sign is going to depend on which body you use, right? Are you using trolley X or are you using trolley Y? But then that shouldn't have an effect on the magnitude, right? So if we use trolley X, right? So we're going to say F net is equals to delta P divided by delta T. Let me explain why I'm using trolley X instead of trolley Y. The velocity of trolley Y, we calculated it ourselves, right? So what if that velocity is wrong and then we use it again, right? There's a good chance that that answer will also be wrong, assuming that there's no positive marking. So let's just stick to trolley X because we're going to be using the velocities that are given to us. So there's no way we can go wrong with the values, right? Momentum final will be 1.2 multiplied by 4. Minus momentum initial, which is 1.2 multiplied by 8, and then divided by the change in time, which I've indicated here in our graph, right? It happens from 20.1 to 20.2 seconds. So here we're going to have 20.2 being the final minus 20.1 being the initial. So if I just, put that in my calculator, let me see what I get here. I'm getting minus 48, right? But we've already said that we don't care about the sign, right? We know that it's supposed to be 48 newtons to the east, right? To the east. And yeah, I think that's it for 4.2.2. Let's see what we can do for 4.3. So 4.3 here is saying that let's determine if the collision is elastic or inelastic, right? And explain the answer by means of a suitable conclusion. So what is the prerequisite for an elastic collision? So if a collision is elastic, then we need two things to be conserved, right? We need the momentum to be conserved, and we need the kinetic energy to be conserved. So in 4.2.1, we calculated the value of y, assuming that momentum is conserved. So it will make sense if we calculate the momentums again, right? Because that's what we're assuming. We're assuming that the momentum is already conserved. So we're just going to calculate the kinetic energy and see if it is conserved, right? Yeah, so let's go ahead and do that. So we're going to say EK before and then calculate that and see if it's equals to EK after. So EK before will be equals to just the kinetic energy of trolley X, because trolley Y was stationary. So when I have 1.28 and squared, right? So if I just put that in my calculator, I have 1.2 multiplied by 8 squared, and that is 38.4 joules, right? And then EK after, now I have 1.2 multiplied by 4 squared, plus this is for our trolley X, right? Plus the EK for our trolley Y. We have the mass, which is what is the mass again? The mass is 0.5, so we have 0.5 multiplied by the velocity, which we calculated, right? 9.6, and then we square that. So let me just put that in my calculator real quick and see what I get. So multiply by 0.5 multiplied by 9.6 squared, I'm getting 32.64 joules. So since, you know, EK before is not equals to EK after, then we deem this collision inelastic, right?